internet screen. Okay, so you can see my screen now. Okay, just checking. Can you hear me?
Yes.
Okay. Okay, let me browse you quickly through what we have already seen before. I recall we are in chapter 2. We are discussing about sensors, actuators, and microcontrollers. We have already discussed sensors and actuators in our previous lecture. And today we'll be completing this chapter 2 with our discussion on microcontrollers. So a quick overview of sensors and actuators. So yeah, so we have seen what is a sensor. Once seen the electronic sensor, computer process interface, CPI, the control system. Yeah, a particular sensor reacts to some, there's a sensing element that reacts to a physical medium. Yeah, this was an important discussion when we have a number of calculations, the transfer function. How do we map a particular value to some voltage level? We have seen it with a complete example. You need to have your transfer function to be able to get a particular value. And then we had a discussion on the types of classes and types of sensors. Can be analog, digital, in this case in terms of position, velocity, temperature, pressure. We have seen a sensor can be classified in terms of contact and non-contact sensors as well, absolute or relative sensors as well, and other ways of classifying sensor in terms of electric, magnetic, electromagnetic, in terms of the broad area of detection, or in terms of the physical law that they use, whether they are using light, magnetic, or temperature, thermal, by its specification, by its application area. So these are different ways of classifying sensors. We have discussed what is a transducer. And our next part of the discussion was on actuators. These perform some mechanical action on the physical environment. We have seen different types of actuators, classifying actuators in terms of linear, rotary, or one-axis, two-axis. Classifying in terms of electrical actuators, hydraulic actuators, pneumatic actuators. Again, these are types of linear actuators, rotary actuators, electric motors. Yeah, we had a discussion on stepper motors and servo motors. This is how a stepper motor works. This is a servo motor, how a servo motor works, the difference between a servo motor and a stepper motor. Motion control in terms of point to point, in terms of continuous path that the motor follow, and connecting sensors to microcontrollers, the different consideration there. Connecting smart sensors to your PC or a particular network, the different consideration there. Yeah, one important discussion on sensor calibration. We have discussed lengthily that before using a sensor, before capturing values, you need to calibrate your sensor so as it gives you correct values. Yeah, this is where we have reached last time. So we'll continue our discussion today with the last part, which is on microcontrollers, and we'll be over with chapter 2. So we had a discussion in the lab as well. We have started discussion in the lab of what is a microcontroller, what are the different parts of a microcontroller. More particularly, we have looked at the Arduino microcontroller. Okay, and you have even been given an assignment on the Arduino microcontroller. With the submission, I guess it is on Thursday this week. Okay, so basically a microcontroller is an embedded chip, which is a computer processor with all its support. Okay, so recall in the lab after you, and for a microcontroller to work, there should be a clocking system, a memory, and I/O built into the device. So what is and you need to make a difference between what is a microcontroller and a microprocessor, or or a PC or laptop that that you use, and how it is different with a microcontroller. So already one big difference is that when we talk about microcontroller, all the support devices like the memory, the clocking, the I/O ports, and everything, they are built into the device. Okay, that is, they are not separated. They are built. They are on, we call it on chip. So you will see it as we proceed. So this is the difference between your PC and a microcontroller on this side. Here on this side, it is an Arduino. So you see here, this is the processor part, the processor. You have your memory, you have your I/O ports, analog ports, digital ports. Everything is integrated on a single chip. The clock and everything is integrated on a single chip. Whereas on a PC, these they are parts, like the processor is one part, memory is another part, the I/O ports, they are another parts. So you see, this is a microcontroller architecture at Mega 168, a microcontroller here, okay, with its processor. Then it has its power modules, its I/O expansion interface, the memory module. Everything is on the chip, integrated on the chip. So a general comparison between a microcontroller, this is a symbol for microcontroller, this is a symbol for microprocessor. Okay, so a general purpose microprocessor contains no random access memory, no read-only memory, no I/O port. So it contains only the processor itself. Okay, so have the advantage of versatility. Why? Because you can add new RAM, new ROM, new I/O port as you wish. Okay, versatility on the amount of RAM, ROM, and I/O ports that you can integrate with inside your computer. As opposed to a microcontroller, it has got its CPU, okay, but the RAM, the ROM, I/O ports, timer, everything is integrated on the microcontroller. Here, the fixed amount on chip. This is what I was telling you earlier. It is on chip. Everything is on chip, integrated within the chip. The ROM, the RAM, the I/O ports. And it consists of less computing power. Normally, it is suitable for very specific purpose with much less cost. Obviously, it costs much less. And this is a general purpose microprocessor. So this is the microprocessor on this side. Then you have data bus and address bus to get the addresses of the different memory location and excuse me, and data bus is mainly for the transfer of data. So you have many chips on the motherboard. Excuse me. So everything is on the motherboard, and your CPU is separated. So this is the microcontroller. So I guess I need to get some water. So here the microcontroller is on a single chip. As I've told you earlier, the RAM, the ROM, and the I/O ports, everything is integrated. For example, a Motorola 6811 or an Intel, the Intel 8051. This is one of the most popular microcontroller that has been used. And you see here a single chip. Everything is integrated on a single chip. So excuse me, let's continue. So here you see the big picture, the difference between a microprocessor and a microcontroller. So you see on the left-hand side, the CPU is standalone. You can add RAM, ROM, I/O ports, timer, or separate. Here, the designer can decide on the amount of RAM, ROM, and I/O ports. A microprocessor tends to be expensive. It is more versatile. It can do different things, whereas a microcontroller is for a specific purpose. This is why this one we call it a general purpose. And you have high processing power on this side. How obviously, because it has high processing power, there is high power consumption as well with a microprocessor. It tends to be typically 32 or 64 bits, whereas microcontroller, the CPU, the RAM, the ROM, I/O port, the timer, everything is on a single chip. Okay, I've already mentioned it before. Fixed amount of on-chip ROM, RAM, I/O ports for application which costs in which cost, power, and space are critical. So you go for a microcontroller. It is single purpose, so it's control oriented, so controlling for specific thing. Low processing power, low power consumption. So these are some characteristic of, and typically it is 8 to 16-bit microcontroller. So here on this slide you see the difference between a microprocessor and a microcontroller. So this is a block diagram of an embedded system in general. In the middle you have your microcontroller. On the left hand side here you see your sensors, and on the right hand side here you see actuators. So, and then you have sensing connecting with the microcontroller and the output interfaces on your actuator. A typical IoT system, a typical embedded system will have those components. We have already seen this in you. Yeah, this is very important. I think in the lab I was mentioning this to you, that normally most microcontrollers, they have they follow either one of those two architectures. This is very important for you to understand what is the difference between a von Neumann architecture and a Harvard architecture. So let me put a question to the class, and I will pinpoint to a specific student to answer the question with respect to von Neumann architecture and Harvard architecture. Observe this slide. You tell me what is a fundamental difference you're able to see on this slide with respect to those two architectures. Okay, so I will ask a particular question for a particular student. Tell me, Evans, Jason, Henry, are you here? You can unmute your mic. Evan, Jason, Henry.
Yes.
So you had a look at the on the slide. So this is the slide, the von Neumann architecture and the Harvard architecture. Can you tell me what you can see as a fundamental difference?
On the von Neumann architecture, the program plus the data is on the memory.
Yeah.
Whereas on the Harvard architecture, the program is only on the memory.
Yeah. And then the data?
It's separate from the memory, I think.
No, the data also is in a memory, but it is on a different memory. This is the main difference. So more or less, okay, what you have said. So I take what Evans has just mentioned here. So in the von Neumann architecture, you notice that the program and the data, they are on the same memory from 0 to n there. They are on the same memory. So it is mixed on the memory here. But as on a Harvard architecture, the program is on one memory and the data is on another memory. So because at the end of the day, you need to save on memory itself. This is still memory, but they're on different memory. And when you fetch your data, so you always use an address bus to refer to which particular address you want to read, and then the data bus will transfer the data for you from the memory to the CPU for necessary processing. So this is in von Neumann, whereas in Harvard architecture, you can see here, so let me here. The program is on one memory, and the data is on another memory on this side. And here we have the address bus for the program, and you fetch. This is called a fetch bus when you're fetching particular instruction that you need to process, because this is program, the instruction that needs to be executed, and then you separate it from the data on down here in another memory. Here again, you use address bus to refer to a particular register, to a particular memory location, and then you use your data bus. Okay, you use your data bus to capture a particular data for processing, depending on the instruction that are being executed. Let me put another question to the class. So Jason has just explained the difference between a von Neumann and a Harvard architecture. a Moda Bacchus, or you're on?
Yes.
What do you think? What is the advantage or disadvantage that we are having between those two architectures? Okay, I simplify your task. So normally Harvard architecture has got an edge. Has got an edge means that it tends to be better in some sense. So can you explain to me how or why?
Maybe in terms of processing time.
Yeah, in terms of the performance, definitely. This is the main advantage of the Harvard architecture, because we are separating the program with the data. This tends to give me improved performance. If someone wants to get unmuted, okay. So this tends to give me a improve performance. I think the difference is on the next slide. We do have it. So have a look here. So we continue. All microcontrollers use one of the two basic design models. That is, either it is a Harvard architecture or it is a von Neumann architecture. Okay, they represent two different ways. Yeah, what is the main difference? Two different ways of exchanging data between CPU and memory. CPU is the processor, and here is the memory. So the von Neumann architecture, both the RAM and the ROM, okay, they are in the memory here combined, and that is the data and the program is on the same memory. In Harvard architecture, okay, the program is on a particular memory and the data is on another memory. Okay, so you will see more difference here. So this leads us to what is RISC and RISC. So RISC stands for Reduced Instruction Set Computers. So instructions are as bare a minimum as possible to allow users to design their own operation, whereas a CISC stands for Complex Instruction Set Computers. So large number of instructions, so each carrying out a different permutation of the same operation. So normally, microcontrollers with Harvard architecture, they are called RISC MCs, okay, and MCs with von Neumann architecture are called CISC microcontrollers. So Harvard architecture normally is newer concept than von Neumann. So in Harvard architecture, database and address bus are separate. Thus a greater flow of data. This is your friend mentioned about time, about performance. So thus a greater flow of data is possible through the CPU, and of course a greater speed of work. So this is the advantage we get by separating the program with the data. So you get in terms of the performance. So we can say comfortably that the Harvard architecture will be faster, will perform better, because they are separating the program with the data, and independently they're doing the data transfer and program transfer. So all of you need to know very well the difference between a von Neumann architecture and a Harvard architecture, and be able to explain. I recall an exam or test question with respect to this. Okay, let me continue. Okay, so this was in terms of architecture. Now you have different families of microcontroller. Okay, I'm not talking about the specific brand like Arduino, Raspberry Pi, or whatever, but this is about the microcontroller. It's the brand for the microcontroller. For example, one of the popular Intel a processor that we use there is an Intel 8051 series, and many microcontrollers have used this particular family. It's based on this particular family. Otherwise, you have ARM32, you have Zilog Z8 series. So you have different families of microcontrollers. So as I told you, this one has the largest number of diversified multiple source suppliers. Intel use it, obviously. Atmel, you see, Arduino, we say that it is based on Atmel, so it is an Intel processor there. AMD and all the others, mostly they use Intel 8051. So you can see here, common microcontrollers, Atmel, Arduino use an Atmel. Intel also has got its microcontroller, microchip, NEC. Motorola has got different microcontrollers, Texas Instrument, this particular microcontroller. Zilog, you have Z8, a microcontroller. These are common one. Most microcontrollers use one of these a processor. And we are particularly interested with 8051 from Intel. So Intel introduced it, you see, quite early, 1981. It's an old processor, but it's only now in recent years that it has got so much popularity. So the CPU can work with only 8 bits of data at a time. It has a clock of 1 to 16 megahertz. It's RAM only 128 bytes. So 4 kilobytes of on-chip ROM, the random access memory, like 4K. It has got 2 timers, 1 serial port, 4 I/O ports, each 8 bits wide. Okay, so these are some characteristics of this particular microcontroller. So it consists of 12 clock cycles. So I think in the lab I give an explanation. So clock cycles, this is what determine the number of operation that you can do, the performance, the number of operation that you can do per second, for example. So application should be run using slower clock speed to reduce power consumption. So the more clock speed, obviously, it will consume more power. Okay, so you have the Dallas version of the 8051 that has got the following characteristic mentioned here. It is 24 megahertz. You understand the 24 megahertz that determine the speed of processing of your processor. So normal processor in your PC, it is in terms of gigahertz. Here we are talking about only 24 megahertz. So low processing capabilities. Even memory, RAM memory is quite relatively low, but this one has got 32 I/O lines, I/O ports. Okay, so quite a large number of I/O ports that you can communicate using those I/O ports with your microcontroller. It can work with 8 or 16 bit. This is a block diagram for again 8051 a microcontroller. Okay, so you see here, this is a CPU, the CPU for the microcontroller, and then these are normally will be on-chip I/O ports, the memory, the RAM, the timers, the serial port, UART, okay, and the oscillator on this. So this is a typical block diagram for a microcontroller. This is a more detailed a diagram for this microcontroller here. So you see the different ports. You see ALU. It stands for arithmetic logic unit. This is where what do most of your computation. Here you can, on this side you see the RAM, on this side you see the ROM. This is just a more detailed representation of this block diagram. Okay, what on-chip facilities it provide? So you have I/O ports, obviously, your system clock. You have a serial port that you can use for data transmission. You have timers and interrupt control. So these are parallel I/O ports that can do input and output. Okay, but you need to tell whether you are using it for input or you are using it for output. So each port can be input or output. So when you are using it, you need to say whether you're using it for input or we are using it for output. When we will be writing our Arduino program, you are going to see that we need to specify this particular port, I don't know, port 11, for example, I'm using it for input, and port 13, for example, I'm using it for output. You will need to specify because they can be used both for input and output. This is a system clock. So after everything is happen through this clock. There is something called the crystal oscillator that gives you the notion of time. We use a serial port, so it's commonly known as UART, Universal Asynchronous Receiver Transmitter. This is the definition of UART, for transmit and receive. For example, to download your data set and receive serially, to download your program on your microcontroller, you will use particularly a serial port. Okay, yeah, when you use a serial port, something very important, and you will encounter this in the lab when we're doing the programming, that is a baud rate. The baud rate is the rate must agree between the sender and the receiver. So for example, you're downloading a program from your laptop to your microcontroller. So your laptop and your microcontroller should agree that will be transmitting and receiving at the same baud rate. Otherwise, what will happen if you're transmitting faster than you receive, you'll be losing data. So you need to set this parameter, the baud rate, at which you are transmitting and receiving. Otherwise, you'll be losing data. And the transmission mode selected using special function register to specify whether you are doing a transmit or you are doing a receive. As after you have internal timers that give you the notion of a system clock, known as TH0, TL0, TH1, TL1, the two timers on the original 8051. Yeah, in terms of the memory, you have different types of memory on your microcontroller, so you need to be familiar with this type of memory. Anyway, I think when you're doing your assignment, the next assignment, you must have encountered those types of memory that the different version of the microcontrollers they offer. So we have one type of memory. So ROM, basically, we are talking about ROM here, read-only memory. Okay, so where you can only store for some you can store permanently, for example, on your ROM. But then you can have different version of ROM. So ROM is a type of memory that does not lose its content when the power is turned off. So it keep it permanently for you in this memory. Okay, for example, RAM normally, as soon as you switch off, power is off, it erases it lose all the information. So for this reason, ROM is also called non-volatile memory. Okay, there are different types of read-only memory, such as PROM. So PROM means programmable ROM. Can be programmed once you store, you program it, you put some data there, cannot be changed once you program it. So it remains there as a RD. So this is a PROM. Where it is here, it is programmable ROM. But then you have EPROM. EPROM means erasable programmable ROM. So can be reprogrammed by erasing the content on it by exposing this memory to ultraviolet light. Where is EPROM? Here. So here you can program it, but you can erase and program it again. Then you have EEPROM. Okay, here is electronically erasable programmable ROM. So the previous one was through exposing to ultraviolet light, whereas this one is electrically. So can be reprogrammed by erasing the contents on it using electricity only. Okay, then you have flash EPROM. So when flash memory contents are erased electrically, so the entire device is erased, in contrast to EEPROM, where you can erase a particular byte, a particular part of the memory. Here, the whole thing will be flashed, will be erased, and you can put new data there. And last type of memory that we can have on a microcontroller is mouse ROM. What is a mouse ROM? So refers to a kind of ROM in which the contents are programmable by the IC manufacturers, integrated circuit manufacturer. They do it, they program it. In other words, it is not a user programmable ROM. You will not be able to add, remove, flash the memory or whatever. You won't be able to do it. This has already been done by the manufacturer, can be done only by the manufacturer. So these are the types of ROM that you may encounter in your microcontrollers. There are different types of microcontrollers. Okay, so anyway, I think in your last assignment you have done an assignment on the top 10. Was it on top 10, if I'm mistaken, microcontrollers? So you may encounter some of these microcontrollers there. So they will differ in their processing CPU capabilities. They will differ in the I/O pins that they offer. Okay, they will differ in the memory that they provide, the amount of bytes for the ROM and the RAM and everything. So they will differ mainly on those parameters: the memory, the processor, the I/O ports that they offer. So most of the time they differ on those parameters only. So now by now you are familiar with some of those types of microcontrollers. You will start familiarizing with this one. That is, we will do this in the lab. But just for the sake of the discussion, I'll put a figure here. So this is our breadboard. So instead of, for us to be able to build our circuit, we need a breadboard for experimentation, basically. Here I've connected a sensor. Okay, this is an IR sensor, infrared object detector. It detects whether there is an object in front of it or or not using infrared. Okay, and if you see carefully here, let's follow the red. You see the red is connected to this particular point here of the breadboard, and I am connecting. If you go down here, I'm connecting this red jumper wire to this port here. So it will go there. It will connect with this one. It will connect with this one. Then this one, it goes to 5 volt. You will notice here after you, these are your power pins. I've mentioned it in the lab. These are the power pins. It goes to the 5 volt. So this is positive. And here, this one, the black one here, from the sensor, it is plugged here. If we go down here, it is here. So this one is connected with this one, and this one on my microcontroller, it goes to ground. GND means ground. So this is negative, positive, negative. For you to form a circuit, you need to have a positive and a negative, the current and the ground. Okay, this is live, this is ground. Okay, so now my sensor is connected, has got power. This is to power the sensor. It needs to form a complete circuit with 5 volt ground. Okay, so here is a reading of whatever is being captured by this sensor. Here it will be read and connected to this point here. If we go down here on this side, I'm connecting a jumper wire. Actually, you could have connected any of those dots here. You could have connected here, here, or on this one. So it doesn't, because all these are connected on the breadboard on this side here. So this is connected here, and this one I'm moving it. I'm connecting it to what? To A0. A0 is an analog input. Okay, is an analog port of the microcontroller. This is an Arduino. You're familiar with this. So this is an analog. It is giving an analog data. It is capturing something. And this is being fed on my microcontroller on the port A0. Then now in my program, I need to write how I read this A0. The value that is being sent by a sensor will be read from this port here. This is again here just to introduce you. We'll do this in our next lab. We are starting to build such kind of circuit to read from sensor and to transmit to actuator. So these are two things that we are going to start to do and to start writing our Arduino program. So this is an IO object detector. I think I have another. Yeah, this is a Sonar object detector. So here, this is an IO object detector. This is a Sonar object detector. This one uses not infrared but Sonar, okay, to detect the presence of an object. If we see the circuit carefully, so you see again this one here, this port here is connected to the ground. Here is a ground. This one here is connected to the 5 volt on this side of my Arduino. So this sensor, they are using the digital pins. You notice here I'm connecting. Recall after you, these are analog, these are digital IO. Okay, this port here is a digital IO. So this is connected to 13, port 13, if I'm not mistaken. It's quite small. And the yellow one, this here is connected to port 12. Okay, so I'll be reading the values mainly from 13 and 12. These are digital IO ports. So we will be experimenting these in the lab. No worries about this. So this was the discussion. Let me show to you now, since we are discussing about microcontrollers, a video, because two very popular microcontrollers that you will have on the market are either it is an Arduino or it is a Raspberry Pi. Okay, let's see a video on the difference between an Arduino microcontroller and a Raspberry Pi microcontroller. Very often we have to decide when you are implementing a system whether we are going for an Arduino, okay, or we go for a Raspberry Pi. So while watching the video, I will request you try to capture the main differences. I will ask questions to the to particular student from the class. What are the differences that you all have been able to observe in the video? So look, follow the video carefully and note the differences that is discussed in the video, and I will ask particular question on the differences. Okay. So you tell me Are you able to see this video with the sound and everything?